So what I want to talk about today is something that we briefly mentioned yesterday, and I said I would give you a bit of a more complete story now. I like standing up, so I tried to be fair on both sides. Well, critical rotation, now what? That's the question. So this is taking forever to change. Are you supposed to change? Yes, I need to point at it. So just a bit of self-publicity. We had this review with Julia, and this is just one of these examples, these Van den Heuvel diagrams that shows all this complex interaction phase, all the way from two stars to potentially gravitational wave merger. And there's a lot of uncertainties in there, and usually, as has been said, there's a lot of attention given to that thing over there. So there's full conferences, full events, workshops dedicated to that. So it's a bit of a breath of fresh air that we're here to discuss this one. But as we saw already yesterday, like the divide is not that obvious, and we end up discussing about everything in the end, because binary evolution involves everything if we're looking at samples of stars. So to get started, that case, more or less the star is being spun up in there. I'm going to do something simple first, or potentially more complicated. I'm not going to put a star in there. And I'll get back to why I'm doing this a bit later. So this is a case where we can expect a non-conservative mass transfer if we have a black hole here, for instance. So we have a bunch of mass transferred through the first Lagrangian point down to the black hole. A fraction of this is ejected, a fraction beta. Sometimes people define 1 minus beta in here. It's a technicality. And what are the typical mass transfer rates? If we have a massive donor, we can talk about thermal timescale mass transfer rates. They can easily reach 10 to the minus 3 solar masses per year. So more or less people were going with this number 10 to the minus 4 for unstable. It's very mass dependent. Now, as we put a lot of matter, we reach a natural limit of the black hole, which is its Eddington limit, usually way, way below this value. When we hit this limit, we're essentially producing so much energy that the black hole reaches its Eddington limit. Its luminosity essentially can push anything away. And in principle, we can eject almost all material out of it, energetically at least. And then if we have this model, if material goes very fast from here, from the black holes to infinity, we have a very simple model for how angular momentum evolves. And we can solve this equation analytically. And it's like a done deal then. We have everything. We know everything about the system and its evolution. Now, it's a bit more complicated than that. We don't necessarily know how much angular momentum is removed on the system. Potentially, we don't know as well if it's fully non-conservative. So just to put a real system in here, this was mentioned yesterday. This is SS433. We have a black hole and a donor star that's about 3 times the mass of the black hole. This is usually used as an argument for stability of mass transfer. There's plenty of uncertainties in this, depending on who you ask. But it indicates that mass transfer can be stable with mass ratios beyond 3, and this need not be the starting mass ratio. The system could have been interacting for a while. And we have this structure. We have these precessing jets coming out of the system. They precess every 160 days. And we have a lot of structure as well in the nearby regions that is thought to come from outer Lagrangian point overflow, for instance. And that affects more or less the angular momentum budget of this system. To highlight that, more or less, here are some results from integrations and more or less calculations in the Roche geometry. Down here, we just have the radius we need to overflow some of these Lagrangian points with respect to the Roche loop radius. I mostly want to focus on the top slide here. We're showing as a function of the mass ratio. So typically, we will be from here upwards, mass ratios of 0.1 upwards. We have that if we consider the angular momentum of the donor and the accretor, the red and orange lines, they tend to be a factor of 2 or 3 below the angular momentum of the outer Lagrangian points. So this affects orbital evolution significantly if we have these extra outflows. Ignore that for a moment. So generally, the idea is that this could happen potentially. People argue that these outflows can be important. If we have very large mass transfer rates, we can form thick accretion disks, and we can have heating in the disk that drives material a significant fraction out of these outer Lagrangian points. And this affects our expectations for orbital evolution, which feeds back into our expectations for the mass transfer rate. And more or less, one thing I can say for you people that are interested in forming black holes through stable mass transfer, at least I've had one of my students, Anakira Pico, sitting there, working and more or less finding that it seems to be robust to these variations in angular momentum loss. So if you want to talk about that, you can check with her. Let me just jump there. Okay, everyone. What about non-degenerate accretor, what we're here for? So we have a star in there that's accreting material, and let me see if this works. Yeah. So how many of you have read this paper? Okay, I would say more of you need to read this paper. It's just a 3-page paper. It's very nice. It's like a textbook exercise. It's really easy to go through. And this is entirely the whole thing with some variations of my own. So the idea of this paper is that you consider a star that's accreting. It has an angular momentum described in terms of its gyration radius. If we assume the gyration radius and the radius do not change much through accretion, we can compute the time derivative and get to that equation over there. We do the same with critical rotation, in particular the ratio of the rotational frequency to the Keplerian rotation rate. And then we do the same thing. We compute the time derivatives. And finally, we assume a mode of accretion. We assume we're accreting the angular momentum corresponding to a Keplerian orbit. And we do the same thing, and we have here coming up this small omega factor on the gyration radius as well. Combine all this, you get to a nice differential equation for how this value evolves with respect to the mass. That depends on the gyration radius. And the nice thing about this, it's a simple separable equation. We have an analytical solution for it, and it only depends on the relative increase in the mass of the star. So if we have a given fractional increase, we have a solution. This is more or less plotting that function for different values of this quantity for a very common gyration radius for main sequence stars. And what we see is that we go up, and once we accrete about 10% of the star, we're at critical. That's the whole argument. That's why everyone cites this paper. Things can be much easier than this. We might need to accrete way less matter. If we have differential rotation, for instance, if the star responds by expanding as well, that helps. If the material does not form a disk, but rather hits like right on the edge, this is something David was pointing out. That can actually bring more angular momentum than an accretion disk. So it makes an important difference. Extra bit detail is if we go very high up in mass, radiation becomes important. A typical correction is this by Norbert Langer, just in terms of the Eddington factor of the star. This is very simplified, though. It doesn't account for darkening. If you account for gravity darkening, actually you see that the critical rotation rate is not affected until you reach gamma equal 0.6, which I guess not many people are familiar with. Now, what happens then? What are our options? So Matthew in his slide pointed out these two already. Option one, the disk feeds the angular momentum out. This is what disks like doing. They bring matter in, they keep angular momentum out. That's essentially their whole deal. So potentially, if the mass transfer rate gets too high and it's not accepting material, we form a thicker accretion disk that can transport this angular momentum and feed it back to the orbit. Option number two, which is the most popular one, rotationally enhanced winds do the job. We're just accreting, we're spinning out, the star can just start shooting up whatever we send it. And option number three, I will get back to it a bit afterwards. So what does this model in particular mean? This is the most popular one. I think part of it is because we have working models that can do this type of evolution that are more or less off the shelf, and we can get that done. We don't have that for the top, although I think there's no fundamental reason to prefer one over the other. So I think that's one avenue to explore. One thing that's nice about this one is that it gives you a kind of self-consistent accretion rate. There's a very natural balance that gives you a variable accretion rate, which might be desirable. This balance is essentially between accretion and tidal interaction. So this is another image from the review we have with Julia. There's thousands of this if you go around looking. There's Matthew was showing his own yesterday. So the idea here is that we have a 20 plus 50 solar mass system at different orbital periods. These are two evolutionary calculations. So on the right, we have the HR diagram. The short period system interacts in the main sequence, undergoes this fast K, slow case A, case B. Long period system, post-main sequence interaction, undergoes one big phase of interaction. Now, one nice way to visualize these interaction phases usually is plotting the mass transfer rate as a function of the mass of the donor. And here we have evolution going to the right. So slow period system, the accretion rate, the transfer rate, the solid line, follows very closely the accretion rate, the dotted line, until just the end, where we have some loss of conservativeness. And this comes because the system widens, tides becomes ineffective in this model, and then the star can be spun up to critical and we're done. Longer period system, the case B system there. We have this rise, we hit critical rotation very early on, and the accretion rate becomes orders of magnitude smaller. So this gives us this sense of non-conservative mass transfer that we expect the shorter period systems to be close to conservative. So yeah, over here. Okay, so this might match some previous work. So we have in here some work with algal systems done by Selma de Mink about 15 years ago. This was not using this rotation model, but rather prescribing, calculating a bunch of tracks, but also varying the efficiency of mass transfer as another free parameter, and then trying to find the best fit to some of these observed systems. And what she was finding is that if you go to longer period systems, it seems to indicate that this efficiency needs to be lower to match these objects. Although there are various caveats, those systems in particular tend to be the worst fitted of them all. So it could indicate some other biases in the modeling. For instance, overshoot is something that's potentially important in here. But this more or less follows the predictions of these models, and you can also see the paper by Kushik that discusses a bit how this goes. But I just want to bring problems. I guess if I'm doing a review talk, I have the benefit of not giving you solutions, but problems. So tides are hard. We already saw from Meng yesterday that things can be very complicated. There's a lot of structure. This is showing for a particular binary at different orbital periods, the circularization timescale. And we see that this can change by several orders of magnitudes once we hit these resonances. And the impact of this is uncertain. The modeling of it is uncertain and very difficult because we need to resolve the crossing of these resonances to have an effective model. Next up, mass transfer rates are hard. So Natasha was showing already that she more or less has this modified model for how to model mass transfer rates. I'm not going to go in detail in this because Jakub is talking in the same session and showing this. The main thing is that we have different methods for the same properties of the donor star. More or less, these are computed in here. And you can see that there's significant differences in the mass transfer rate, factor of a few. And if we don't understand well how mass transfer is going, we don't know well how these streams move and can potentially either form accretion disk or undergo direct impact into the star, and that affects the angular momentum budget that goes. So these are issues that are more or less potentially in the technical calculations. So the model might be right, but it might be very hard to have good predictive calculations. But the next point I'm bringing up is more fundamental. It's the point where this breaks down. And that would be that it might be impossible. And this is the reason why I brought the black hole first. When you have a black hole, you will have a very efficient engine that can give you lots of energy to eject essentially whatever you want. If we don't have a black hole, we need to rely on the luminosity. And if we think about radiation-driven winds, we have a fundamental limit that's called the photon tiring limit, which means we're putting all our luminosity into unbinding matter. So if we assume we're removing from the surface of the accretor this material, critical rotation just gives us half the energy we need. That doesn't mean it's unbound. So we need the other half of GM over R to get out. And this gives us a limitation on how much mass we can drive out as a function of the luminosity. If we are very generous, we can consider that the matter is removed from the outer regions of this disk, essentially it's Roche law, and that we're using all the luminosity of the stars. And this is very extreme. The binary would be dark if we're taking all its radiation to kinetic energy. So does this limit come into play in simulations that we have? It does. So this is another plot by another part of the work by Kushik. This is just a set of simulations for a fixed donor mass, around 20 solar masses in this case, different initial mass ratios, different orbital periods, and the coloring more or less marks different outcomes. I won't go into a detail of all of them, but mostly point to this green side in here, which is a whole lot of the parameter space where we're hitting this limit. So it seems to be very, even if we believe this model, it seems a whole lot of systems actually hit this boundary, and this could potentially drive mergers in these early stages before we form a compact object. And just to say, what happens here is very uncertain. We don't have the energy. Maybe we start draining the orbital energy out of things. Okay, so very quickly, how do we go from here? This is just a very quick summary of things we can do. Observing binaries, we have nice binaries that are resolved. This is Beta Lyrae. It's actually undergoing the fast case A mass transfer, and we can observe it with Chara. Next up, strip stars. See the talk by Tomer. Essentially, that's all I'm going to say. And we have B X-ray binaries that are potentially indicative of not highly non-conservative, that's a weird thing to say, mass transfer into the accretor star. Okay, on the theory side, just to finish here, I'm gonna bring just the overused trope of the spherical cow in here. And I wanna bring this just to say that this is not a distinction between rapid and detailed codes. The detailed codes are still 1D codes, and we're dealing with 3D hydrodynamics problems here. So in a sense, we're almost as limited as these detailed codes. The only thing we do better is get the thermal response of the star during these phases. So we need to move from this, but I'm not gonna say we need to move to perfect 3D calculations. We need to essentially move to like low poly 3D. Like it's not gonna be high fidelity. We're gonna need to cut corners. So make plenty of assumptions that will make us uncomfortable, but at least gives us a physical insight into what's happening, what could be going on in the systems. And I just wanna end up by highlighting that an important part of this is working out initial conditions. And this is just a note to the work of another one of my students who's been working on implementing tidal deformation in 1D calculations. So essentially following the work on the implementation of rotation, allowing us to compute evolutionary models that include tidal deformation by considering average over the Roche potential, similar to what Natasha was talking about yesterday. The nice thing about this is that the models can be very naturally reconstructed into their 3D structure as initial conditions for binary evolution. And that's the last thing I wanted to say. So thank you very much for your attention.
Thank you so much, Pablo. We have about 10 minutes for questions.
Thanks, Pablo, for a great talk. So, I mean, you mentioned a bit in the end that also 1D simulations aren't perfect. And of course, there you also make, say in Mesa, you make assumptions about like overshooting and so on. So I was just curious about your opinion. Like, do you think for most problems, ideally, we should be like exploring some like a parameter space with Mesa models, or in most cases, we're fine?
I would say
by theory.
Most problems that are really hydrodynamics problems are the ones that Mesa does not do well. So if we have good reason to assume in a given situation mass transfer is conservative, I think we're safe. We can use Mesa for that. Once we're hitting the realm of non-conservativeness, potentially because we reach critical rotation, that's a very thorny regime, and I think we need to be very careful about trusting our models fully.
What about magnetic fields?
Well, so some people are potentially thinking that magnetic fields might form in this situation. That could be, for instance, something that could drive angular momentum out. For sure, you have magnetic field effects in the accretion disk itself. So this is essentially what can help propagate the angular momentum outwards. Magnetic fields on the star itself, I don't know, maybe it starts operating a bit like magnetic braking. So that's something that acts on low mass stars, and that essentially drains angular momentum from the system. So it ejects it, and that essentially would potentially kill your binary.
Okay, yeah. Instead, uncertainties on binary evolution aside, what do you think can be improved in stellar modeling to help with this problem?
I think it's going to be a calibration game. So that's why I was pointing to the observations. I think we just need to try and calibrate it and do our best with that. But fundamentally, we can do 3D hydrodynamics, and this is a 3D hydrodynamics problem. What's happening in here? I think we can get simpler physical pictures, but they're always going to fall a bit short if we want to be really quantitatively accurate.
Do you think that our prescription for, I don't know, rotation in Mesa is working fine at least, or we can improve also that part?
It depends on what aspect. I think deformation, for instance, it's well treated even up to high rotation. Some people might disagree with me there. What's very uncertain is the formation of other longer timescale hydrodynamical processes such as meridional circulation. That still remains extremely uncertain.
I wanted to ask about the photon tiring limit. Do you really need to get all that energy though? Because the material not accreted might not go all the way to infinity, right? It could sit, as Rogero said yesterday, in a circumbinary disk. They're still pretty close. Do you can you account for things like that when doing the energy budgets for the amount of mass that is coming?
Well, I guess you can try and compute if it needs to go to essentially a circumbinary disk. You have an idea of the minimum radius for stability of the circumbinary disk. It's still going to be much larger than the size of the star, for instance. So I think just because it's 1/r, it's still going to be a significant amount of energy.
Yep, really nice talk. I have a few questions, I guess, but just one quick one is so you said for the non-degenerate accretors, you say that the radius of gyration and the radius of the accretor stays constant, and I was just wondering how reasonable that is as an assumption. Yeah.
So I wanted to show people this because that's an assumption of the Bucket paper. It's argued actually that that goes in the way that you need more mass to accrete before hitting critical. So a star that expands actually expands in a way as it transfers mass that it's the outer layers that do so. And this lowers the gyration radius significantly and essentially makes it easier to hit critical rotation with less angular momentum.
Okay, thanks. Do we have any other questions?
Yeah, I was just curious. So you mentioned in the end that like you're gonna look for like the deformation, tidal deformation. So I was just curious, like, do you think that will also impact like things like how much you can rotate up the star, like spin up the star, like total mass transferred like significantly, or not so much?
I wouldn't think in most of these cases, I don't think it would be that important because in many situations, this star is well inside its Roche loop. So it's more or less operating in its own potential. So at least to that part of the problem, I think it's not going to be important. Something we're exploring is whether or not these tidal deformations, for instance, impact stability of mass transfer. But that's a different story altogether.
Yeah, really nice talk. You mentioned that the hope is calibration, so we need observations. Do you have any observations in mind that you would hope to see? And the second question is, you also mentioned Eddington sweet circulations, and that is like actually kind of hopeless. But I know you worked a lot on chemically homogeneous, the evolving stars. Do you think we can't actually calibrate our models to observations of chemically homogeneous stars before we do hydro simulations, or do you think nah?
Well, I think that I think the best is try to calibrate things in well-separated regimes where we know one thing is acting. So I guess all this chemically homogeneous stuff is expected to operate in the upper main sequence. But for mass transfer, I think we can get a lot of physics. Even if we care just about massive stars, we can look at intermediate mass stars, and they're going to have very similar physics. So one kind of system that I'm very interested in is these impostors, these really immediately after mass transfer systems, because they're showing the properties after the end of this rapid mass transfer phase. And in some of those cases, we see very extreme mass ratios. And it would be very hard to reach those if we don't have significantly conservative mass transfer.
Pablo, very nice talk. I'm wondering, like, how do you think of, because MESA has probably like 1D hydrodynamics, like modeling like massive star shocks. Or could that be another maybe quick like solution for doing like a more self-consistent like hydrodynamics, like when running binary? I know that's for like modeling like supernova shocks, like massive star like shock explosion shocks, but like maybe not quite like reach our like binary.
Yeah, so I think one potential avenue to improve this, more or less, David was talking about this, is essentially, I was talking about this, well, I'm not going to go all the way back to the slide. These Lubo and Chu calculations from the 70s, that they were really doing these calculations of the motion of stuff in the Roche potential. Some people might be horrified to know that we actually use fits to those calculations from the 70s, that we could essentially just compute trivially in our laptops. So that's one way we could improve at least one aspect of the models, understanding how the stream moves through the system. The more general hydrodynamic problems, I think we need to construct a physical picture that operates in terms of these 1D things. So it's going to be tricky. So I guess maybe a pointer for you as well, because I was mentioning tides are hard. And I think it's also much harder if this thing is significantly deformed at critical rotation. We need to essentially understand the forced oscillations of a significantly deformed star. So it's even harder.
Yeah, like 1D spherical symmetric is a basic assumption, but like if it's no longer like spherical symmetric, we need to rebuild our code maybe.
So yeah, I think you actually were starting to answer the question I had, but maybe more generally, you've mentioned calibration a few times, and I'm sort of just trying to imagine, is this calibrating a few key parameters in existing MESA implementations, for example, or I mean, do you imagine needing to develop more sophisticated treatments? I mean, is this like a coefficient for Eddington Sweet that we just calibrate against observations, or broader than that?
I think we need to think. I think there's also a very philosophical question of whether or not we're doing physics at that point. I think it needs to come as information that would motivate a more physical model. Because I think we need more physical constraints to actually develop a model rather than start thinking in the clouds what should be happening. I think that's at least my view.
I think we have time for one more question, if anyone has one.
Helium?
I wonder,
wait.
Sorry. Yeah. So it has been mentioned several times, there are two ways that inefficient mass transfer can happen on the accretor. So one is this critically rotating accretor just emits the accreting matter via radiation power, and the first is this feedback. So MESA currently has the second option. So I wonder if MESA has a potential to implement the first option and explore this alternative option.
Yep. I think there's no fundamental reason it cannot be done. So someone needs to come in and do it. Or if I get bored at some point, I might just end up doing it myself. I guess that's the status of it. But in principle, one can do something very similar. Like the way we do this is that we adjust the mass transfer rate once we hit critical. We could instead adjust the amount of angular momentum that's being accreted once we hit critical rotation. So I think there's the potential to do that and have a comparison. One tricky thing is that will give us just fully conservative models. So it better be that all binary evolution is conservative, otherwise that won't work.